Let's talk about random variables and probability distributions for normal distributions. So a normal distribution are continuous. So we're talking about continuous variables. And when you plot the data, remember under here are a whole bunch of rectangles. And when you plot, they are bell-shaped and continuous. And they approximate the distributions of many different variables. So these are very useful distributions for inferential procedures, which we're gonna do, and are distinguished from one another only by their mean and their standard deviation. Because underneath this curve is still probabilities, this area underneath this curve is equal to 1. All right, so if we have an example here of some data with the mean at 100, notice the value of the mean, mu, is the number on the measurement axis lying directly below the top of the bell. So in other words, the mean cuts this data in half. And of course, you can see if you have a standard deviation, you can find these values. If one standard deviation is 10 units, then one standard deviation above would be 100 plus 10. One standard deviation below would be 100 minus 10. And if we were two standard deviations, we'd do 2 times 10, how we get plus the mean, and so on. So the distance to either side of the mean here changes. You can notice the curve is changing from turning downward to starting to turn upward. So the standard normal distribution is where we're going to standardize our mean to 0 and our standard deviation to 1. Now, why in the world would we do that? Well, the problem is if you are looking at something with baseball averages, and you have all the different baseball players in here, and you have the population average or the sample average, and then somebody else says, well, I want to do that same thing, but I want to look at basketball 3-point scores, And so as you can see, they're going to be different means, so we need a way to standardize this so we don't have to keep using different formulas that we're going to end up using a table to look up probabilities. Now, this curve here, this normal distribution, a lot of times you will see it called a z-curve or a z-distribution, where we look up z-scores. So this z represents a variable whose distribution is described by the standard normal curve, meaning a mean of 0 and standard deviations equal 1. So instead of calling these x values, we now call them z values because you look them up in what's called a z-table. So the table of areas under the standard normal curve is used so we can actually calculate probabilities of particular events. And so once we standardize our data, we can use the table for anything: baseball, basketball, football, light bulbs working correctly, anything in the world, as long as we standardize our data. So we end up looking at these z-scores, as they're called, in a table. Okay, so if I'm looking at a z-score, and we're just going to call it this z-star, and I'm looking from negative 3.89 to positive 3.89, you can find all of these probabilities in the table. Okay, if you don't even have the book, all you have to do is Google a normal distribution table, z-scores, z-table, normal distribution z values. And so if we're looking at the area under this curve, so under the z-curve to the left, then as I mentioned in the previous lecture, the less than or greater than gives me the same thing, where we use this z to represent a random variable whose distribution is the standard normal distribution. So what we do is when we look at this table, you can see, and you're going to see an example here in a minute, but if you're looking at yours, the row labeled with the sign, this z star, and the digit to the to either side of the decimal point is how we find the whole number and then the first decimal place. So like negative 1.7 or 0.5. Then the column gives the second digit. And so you're looking at a row, an intersection of the column, and where this intersection is, that gives you an actual probability. So let's see if we can figure out how to read this table. So if we're interested in the probability that z is less than 1.42, all right, well, I look up in the table and I find this column here, or this row, I should say, for 1.4, and then I go straight across until I'm under 0.02, because if you add those two together, you get 1.42, and that gives me the probability, which is this area right here. So in other words, for this standardized z-curve, the probability that I would get the random variable 1.42 or below would be 0.9222. Now think about it. By looking at this curve, I said the mean cuts the data in half. So that would say if I cut this data in half, let me get something to draw with here. If I cut this data in half, pretending I can draw a straight line, then that means 50% or 0.5 of the data is below here, and of course 0.5 is above. So you would expect this number, because if I'm going to here, that's already half the data. So now I'm just adding this piece on this side over here. So you want to get where you don't just look things up in a table, you want to be able to say, yeah, that makes sense because it has to be bigger than 0.5, okay, to be able to see that I'm already past half my data. All right, suppose we are interested in the probability that my z-score is less than 0.58. Well, once again, I get my table, I look at 0.5, I look at 0.8, and I find my intersection. Okay, so again, if I go back to this example, the 1.42, you would expect this to be a lot more area than the 0.58. And again, it's above half the data, so that makes sense. What if we're interested in our random variable lies between two z-scores? Well, if I actually get the area to 0.58, which was that 0.7190, and then I get my area to negative 1.76, so I find this area, I could subtract the two and that would give me my middle area. So whenever you want some in between, you just take the larger z-score minus the lower z-score, and that gives you your area in the middle. Suppose we're interested in the probability that my z-score is greater than 2.31. So greater than. I look up in the table 2.31 and you say 0.9896. However, your table gives you the area from minus infinity all the way out here up to that z-score. If I want this area, then I would take and subtract 1 minus the 0.9896. And why 1? Because all the probabilities have to add to 1. So if I want to find greater than, or the area to the right of, then I need to take 1 minus. So in other words, this 0.9896 is all this white area here. So to get the area on the other side, I take 1 minus. Well, instead of these z-scores, let's say I want to actually find the z-score that's the bottom 2% of our population. Maybe I want to know the bottom 2% of my students, okay, who fall in this area. So what I'm looking for is my z, okay, is less than some z value. This is opposite of what we were doing. And I want to find 0.02. Within the table, these 4-digit values are probabilities. So 2% would be 0.02. So what I do is I look for the value that is the closest to 0.02. Well, I can see it looks like 0.0202 is the closest. And many times you may not get exact, like in this case, so you pick the closest value. And then I read the z-score, so I get negative 2.05. Again, this would make sense that this would be negative because I'm to the left of 0. Okay, so remember, these z-scores are the number of standard deviations you are away from the mean. So I'm below the mean, negative 2.05 standard deviations. Okay, so as mentioned, if I have some data, okay, and I see that I have a normal distribution, then I can standardize. I can take and standardize my mean to 0 and my standard deviation to 1. So if x is a random variable whose behavior is described by a normal distribution with mean mu and standard deviation sigma, then if I want to find the probability that my random variable is less than, okay, so less than some value here, then what I'm doing is I'm standardizing it and looking it up in the table. Works the same way if I'm looking for a value greater than or in between. So what I'm doing is I'm taking this z and I'm creating a standardize, okay, so that's my z-score, and how I do that, I take my data value minus my mean and divide by the standard deviation. Well, in this case, this a lot of times can be, it may not be an individual data value. These might also be like the sample mean, so like x bar. Okay, and so what I want to be able to do is I want to be able to standardize any other data into z-scores. Again, why? I don't want to carry around a table with a mean of 14. I don't want to carry around a table with a mean of 300. I don't want to carry around a table with a mean of negative 5. So in other words, if I can standardize my mean to 0, and my standard deviation to 1, all I need is that one z-score table. All right, data on the length of time to complete registration for classes using an online registration system suggests that the distribution of the variable, x equals time to register, for students at a particular university can well be approximated by a normal distribution. This is important because this says I can find probabilities with my z-table if I standardize. This is with a mean of 12 minutes and a standard deviation of 2 minutes. I want to know what is the probability that it will take a randomly selected student less than 9 minutes to complete the registration. Well, again, I don't have a table with z-scores where the mean equals 12. I have one where the mean equals 0, so I standardize it by taking my data value that I'm interested in here, and I can certainly see it's below the mean, so I should get a negative z-score. I subtract the mean, and I divide by the standard deviation. So what I'm doing is I'm standardizing this 9 so I can look this value up in my table. So what I do is I look up negative 1.5 in my table to get my probability, and I see that I get, if I'm looking in the negative z-table, I get 0.0668, which would make sense that it would certainly be way less than, it'd be less than a half because the half is at the mean, but it's just this little area right here. Well, what if I'm looking at what's the probability that it will take a randomly selected student more than 13 minutes? So this is to the right, this area to the right side. So I still do the same thing. I still standardize this. And when I standardize, I get 0.5 that I have to look up in the table. But remember, the value you find in the table, because it's to the right of it, I'm going to take 1 minus, because the 0.6915 is all of this area here. So if I take 1 minus, then that gives me this area. How about the probability that it will take a randomly selected student between 7 and 15 minutes? So now this is an in-between probability that I'm looking for. So actually what I have to do is I have to standardize the upper value, 15, and I have to standardize the bottom. Okay, so I've gotten my z-score for 15, I've gotten my z-score for 7. I look these values up and I subtract the two, because remember we said how you find the in-between is by subtracting the values. So this is important that you can understand and go through all of these examples, that you understand how to read this table to find these probabilities once you have standardized your data.